Good afternoon, everybody. Thanks for coming to this seminar. Today we are very honored to have Professor Zongjin Li to visiting us and give us a seminar titled "Advanced of the Building Material Techniques under Guidance of Physics." So I think many of you know Professor Li very well. So I just give you a very brief introduction. Professor Li is a distinguished chair professor at the Macao University of Science and Technology. In fact, he obtained his bachelor degree from Zhejiang University and then went to Northwestern University in Chicago and got his PhD in 1993. And he is an honorary member and fellow of American Concrete Institute, honorary chair of the China Group of RILAM, and the founding president of ACI China chapter. And he has, in fact, secured a lot of big grant. I think one of the very prestigious grant was National Key Basic Research Project, so-called 973 973 project. I think Professor Li was the leading investigator of that project. So he established the prestigious Golden Research Conference series, Advanced Material for Sustainable Infrastructure Development in 2014. This is also a very prestigious conference. So I think in future, maybe you have opportunity to join this Golden Research Conference. So Professor Li is the author of 5 technical books. One of them, maybe many of you have it on hand. This Advanced Concrete Technology, which is sought after resources in various national and major university libraries. So he has produced over 400 technical papers with a Google Scholar citation over 34,000. And he has an H index of 101. It's very high H index. He also holds 8 US and 20 Chinese patents. So Professor Li's outstanding contribution to the field have been recognized with very prestigious Arthur Anderson Medal, this award from the American Concrete Institute in 2017, and the Distinguished Visiting Fellowship Award from the British Royal Academy of Engineering in 2014. So without further ado, let's give a warm welcome to Professor Li. Yeah, please.
Okay, thank you.
Yeah, I think you can take a seat.
Oh,
yeah.
Okay. I try to. Okay. So good afternoon, everyone. It is my big honor to come to the Hong Kong City University to introduce some my previous research output. So I will thank Professor Dai for his warm invitation, and also thank Professor Xian for his detailed arrangement for my visit. And also thank Professor Yu and take his student from Hong Kong U to come to this seminar. Okay. So today, okay, I think, okay. So today, okay, I will give a brief talk regarding to how to utilize the guidance of the physics to, okay. To use the develop of a material technique, especially in civil engineering. So this is my outline for the the lecture here, and first I give to the introduction. Okay, why we have utilized the guidance from physics to guide our the research in the material, and then I talk about the several the specific case. One is for this nanoscience and nanotechnology, how we can utilize the principle to a direct our the research in material. And then I specifically talk about several innovative material and how we, according to the mechanism of this physics, and to develop this material. And next, I will talk about the experiment method. So this is another area for the application of physics to develop this kind of innovative experimental measure. So finally, I'll give the brief introduction regarding the development of the new the wind power generation. Okay. So we know many of the English words it come from Latin, from Greek. So the physics, okay, is from the Greek. In the ancient is the Greek. The meaning is knowledge about nature. Okay, so this is of course the natural science is not a social science, and what is specific doing is study the matter and its motion through space and time. Okay, so the physics mostly is related to the energy and the force. Okay, we know that our human being, okay, get is the big achievement is and is the theoretical breakthrough of physics. So here is a few examples. For example, for the electromagnetic, this kind of theory let us to develop a TV and a computer and the electricity generation. Okay, and this the fundamental understanding for this electromagnet. And then for the nuclear physics, okay, after we are using the good understanding, we develop something like nuclear weapons, and also we have a nuclear power plant, these good things. And recently, we have a so-called man-made science, okay, it's for the fusion, reaction of the atoms. For the mechanics, okay, we have the calculus, okay, it's based on the development in the physics. Okay, so this is in the physics, there's one branch we call applied physics. Okay, this applied physics basically is intended for the technical or practical applications. Okay, so the applied physics is bridge the physics and engineering. So this applied physics can get the application of physics in the various technology, include the material development as I talked today. Okay. So at least some example like the biophysics, chemical physics, engineering physics, material physics, nanotechnology, and quantum chemistry. Okay, so these are all the application of this so-called applied physics in the different area. Okay, so now I move to the first application of the nanoscience and nanotechnology. So for this, okay, nanoscience and nanotechnology, okay, so first we notice this nano, okay, so that's regarding the scale, okay. And in the science, it always refer to the something is exists and we are discovering its nature. And the technology is something we have to create in the world. For example, the buildings, okay, the railway, okay. So these new things we have to create. So I more prefer the second the definition. Okay, with the nanoscience dealing with the manipulation of the material at atomic and molecule scale. Okay. So basically, it involved material structures and material property at this small scale. And nanotechnology is the ability to observe, measure, and manipulate, assemble, and control, and manufacture metals at this nanometer scale. Okay. So basically, this there's the definition. Now, back to our civil engineering. We know that, okay, we have utilized the concrete for our construction, and the concrete is a very typical multi-scale material. So at this the angstrom level, we have a molecule structure of this CSH gel. It plays very important role to glue all the individual particles together to form our solid concrete material. Okay. So in this time and length scale, okay, our you see the nanoscience will be you see the focus for this the formation, hydration of this cement and the formation of that hydration products, especially for the CSH. Okay, for this the nanoscience, okay, there's the base, of course, is from the physics. Okay, we know that we have Schrödinger, okay, in Chinese, you see the Schrödinger equation. Okay, so this is a very beautiful differential equations with the H is the operator and the psi is a wave equation and the E is the potential. So for this the autumn, we can distinguish divided this equation into something you see regarding the nuclear core, okay, another regarding to the electron, okay. Compared with the electrons, nuclear core is a huge and very stable. So most you see the calculation is focused on the electrons, okay. However, there's still a problem, even we are separate the nuclear core and the electrons, because the wave function, okay, is a function of 3n variables. N is the number of the electrons, okay. So it's very complicated. So after so many years, there's many you see the method, use the matrix, you see the stability, but cannot give a very good solution. So until okay in the 1960s, okay, so we have this the so-called new theory, we called the density functional theory developed. So in this theory, it simplified to the electron calculation into the electron density. So in this case, you reduce the 3n variables into 3 variables, x, y, and z. Of course, we ignore the, you see the self-spin of these the electrons here. So when we calculate the energy, okay, we divide it into the 4 parts, okay. So 3 of the parts is the kinetic energy, is the energy and the economic energy between the electron and the only you see the unknown is EXC. Okay, so this we have to resolve this so-called you see the correlated exchange energy. So there's basically 2 ways, or one is a local, another is like a global. We have LDA and GGA. So basically there's a 2 approach to solve for the EXC. So once EXC obtained, and then this problem was resolved. Okay, so this is some very fundamental knowledge. So basically, or currently, we can use a theory, so-called DFT, okay, and then we use some algorithms, okay, including the many like the plane wave, okay, action correlation function, and then we can utilize this to get the initial structure optimized, and then we use the AB initial method to do the calculation of this. And finally, we can get this surface energy, change status, and the reaction pathway. Okay, so this is the route for us to use the quantum mechanics. Okay. So specifically for our, you see the civil engineering, okay, so we are mainly concerned so how to establish the CSH, the use the mystic structures with AB initial simulation. So from there, we see we can have this cement component, especially C3 or the is a calcium silicate when they plus with water. So what happens is that the water will be attached, okay, will be on the surface of this. Okay, so we call the absorption. After absorption, okay, so some you see the oxygen in the water, okay, will pull the calcium ions from this C3S, and then meantime there's some you see the hydrogen or the protein getting in, so we can form the CH in the solution and CSH on the surface of this C3S. So that's about nanoscience. Now we talk about nanotechnology. In the nanotechnology, one of the big tasks is to produce the nanoparticles. So when you produce the nanoparticle, there's two ways. One is top-down. The top-down is that you have this large size piece, and then you use mechanical, thermal, or the optical, okay, use all this like a chemical, okay, method to change the large size into the very small size. We call this top-down. Another is bottom-up. The bottom-up is you start from the atom and the molecules. Okay, also use the different is the chemical method, and to assembling this atom and molecule into this nano particle. Okay, so basically we have these two. Okay, how about for the concrete engineering? Okay, for the concrete, okay, we said this can be nano engineered. When we talk about engineer, that means you do something on the purpose. So nano engineered, that means we do something at the scale of nanometer. Okay. So how we do this? Usually we can use some is a nanoparticle, okay, and then we use that to react with some you see the hydration products, okay. After you see the reaction, we will change the material structure from different from the hydration material structure. With this change of material structure, we can improve the mechanical property. Okay, so basically the nano engineering for the concrete is doing things like this. So currently we have mainly you see the nanoparticle for example nano you see the silica, you have nanotube, nano carbon tube, and nano titanium, and graphene, and also the monomer. Monomer is the organic material before the polymerization. Okay, it's very small in size in this. We'll give one example to do that. Now I move to, okay, I said in the civil engineering, one of the big, you see, the target of nanoscience is to reveal how the CSH is formed. Okay, so for the you see for the formation of CSH, there's many, you see the step. First step is when the water contact with the cement particles, the water molecule will be adsorbed on the surface of. So there's many, you see the research, at least here, but they are not very complete. So in my, you see the group study, so we are trying to fully uncover the adsorption mechanism of water on the C3S surface and understand the stability of molecule and molecule adsorption and dissociative you see the adsorption. Okay, so I will talk about. So this work have been done when I moved to the University of Macao. Okay, so one of my students, I have 3 students doing this work, and the best one is Zongjin Li. Okay, he did very well. Okay, so for to study the water absorption, first, okay, he should be okay, get the back, you see the optimization for the C3S. Okay, and then you do the surface cleavage. Okay, so you cut under the surface, and then you see the calculate the surface energy, and then he studied is the isolated water, a single water molecule, and then the bulk is the water absorption. Okay. As I mentioned, we utilize this the quantum mechanics. However, here to increase the number of the atom, so we are extended into this MD molecule dynamics. However, we utilize this the DFT. Okay, the software called VAST. So we use that. Okay, we get the potential. So this potential is have the you see the accuracy of the quantum mechanics. Okay, so we use that potential put into this the MD simulation. So we call the ARMD, or the AB initial molecule dynamics. So that means you have you see a more you see the atom can be put into the system, but you have the accuracy of the quantum mechanics. Okay, so this is so by utilize this, okay, so we have first, okay, to study this different UC type absorption. Dissociative absorption means the water molecule is separate into the H and OH, okay, and then observed on this surface separately, okay. And the molecule absorption means the whole water molecule, okay, on the surface of this C3S. Okay, so we are already studied what is the strong, you see the absorption or the weak, and what there is you see the characteristic. Okay, by utilize this the AI MD simulation. Okay, and all this the strong, you see the absorption is related to the charge, okay, transfer. Okay, so we are always found, okay, around this the oxide oxiding side, we always have this the higher transfer of this electron. There's a big difference. I use this the right you see the number listed here. So this is there's a fundamental mechanism for this. So And then, okay, we can see for the, you see the absorption of the water. Okay, so basically, okay, they can, you see after you click on surface, there's a change in the energy. Okay, but this overcome this the energy. You see the barrier, and then you can move to the next step, and then finally you got the molecule observed on the surface. So after that, we studied the dissolution of this calcium into the liquid. So the dissolution of the, you see the calcium, well, we can see, okay, for example, we know that the limestone, okay, if you go to the cave, you know there's a dissolution. You have the water drop with the calcium inside, and that's how it formed this. And we have the drug delivery. There's many things regarding with this. However, what we are trying to do is we trying to do for the cement material. So we want to simulate this complete and more realistic process of calcium dissolution from this the C3 surface, and then we are quantitative using the calculate the thermodynamics and the kinetics property of this. To do this, okay, in addition to this two software, one is you see the what, another the CP2K. We need one more, because for the CP2K, okay, they cannot you see the pass this the higher this the energy barrier, okay. So we need a so-called meta dynamics, meta D, okay. So meta dynamics 中文我说有时我们就翻译成这个超级动力学Okay, so in this metadata, there's two things. Okay, one is that you see the sampling rate. So they are increased sampling rate. So every smaller delta, you see, they have is the sampling. And the second, they provided so-called bias potential and put this potential into this the ARMD. So with this is the bias potential, the originally, okay, for example, you have the ball in the valley cannot cross over this the peak, but with this bias potential, the reaction can happen, so they can go cross this energy barrier. Yeah. So after you see the is so-called the absorption. Okay, we know that on the surface of the C3S, okay, there's some water molecule there. Okay, so this water molecule, especially there's oxygen. Okay, you have you see this formed the bond with the calcium already. Okay, so here we are utilize you see the two common keys. One is calcium alpha. Calcium alpha means there still have three oxygen from C3S is connected with calcium, and the rest is from the water. Okay. Okay, so we can calculate from a different. So here you can see we from A to B. Okay, so from there you can see original. Okay, it have three. You see the oxygen from the C3S connected with is calcium, and the two is you see the water, and then you see the after you see the they cross the barrier between A and B becomes stage B. They have one more oxygen from water. Okay, and gradually you have an increase to 4, and then the connection of this the oxygen from C3S with the calcium reduced to 2 and reduced to 1 finally resolved. So in this calculation, okay, on the top, this the red means the energy, you see the barrier is overcome, And the bottom means the total energy change between these two states, between A to B and B between B to C. Okay, so these are all the things. Now we are calculate the CA beta. CA beta means you still have a strong connection with the C3S is the calcium. Okay, 5 oxiding from C3S connected with it, and only you see the single from the water. So similar, okay, calculation, okay, from A to B and from B to C. So you can see with the increase the connection with the C3S, the oxidation gradually reduce, and the connection with the oxidation in the water gradually increase. So that means this the calcium gradually detach from its cement particle and gradually move into this liquid. Okay. So here we showed, okay, in the center we have one is a very nice. You see the TEM the photo. Okay. So basically you can see the black one is the particle of C3S, and you can see away from there is a lot of you see the black spot. So that is you see the calcium, okay, or the calcium hydroxide. Okay, so this kind of verification from experiments. Okay, and this graduate so that mentioned, okay, with the you see from absorption, and then you have this the connection with the oxygen from the water, and with the increase connection of the oxygen from the water, the breaking the bond between the oxygen from the C3S with this oxygen, finally they can move it out. So this is the process. Okay. Okay. So after this calculation, okay, based on my understanding, okay, so the CSH should be formed on the surface of cement particle. Okay, we have a lot of, you see the examples from experiment. Okay, so for example, this is some, you see the photo from one of my students from HKUST. Okay, so he took a very nice, okay, you see the after you see the hydration, okay, C3 particles still in there, and outside on this move we can you have this some so-called internal CSH, and for this, okay, and outside is out CSH. Okay, so there's some use TEM. Okay, they change from this. Okay, so according to you see the you see the arrangement, my students should you see the doing the calculation, concentrate on this the C3S surface, but it's very difficult. Okay, so my students at that time, you see the get another way. Okay, he did the calculation for the assemble of this calcium and the silicate. Oh, there's a meaning. Okay, we know that we have so-called you see the reaction. Okay, the secondary formation of CSH. Okay, so the 火山灰反应. Okay, so in that case, that's exactly like say. So you have assembly of this calcium and silicate. Okay, so I said, okay, your work is also good, but not really for the CSH for the formation on the surface. So he did this, okay, and also he found two very stable combinations of you see the calcium and silicate, and also they continue to let this the combination of this silicate and calcium continue to join together, form so-called secondary CSH. So this part I going to utilize because currently, okay, we need to reduce the carbon dioxide. So one way to reduce the carbon dioxide is to eliminate Portland cement. But we eliminate Portland cement, we need the binding material. So what we can get this the calcium, I can get the silicate from natural source, and also can from industry waste. And then we use this get that reaction, okay, to form so-called secondary, okay, CSH. Okay, so this is still good, okay. But I still ask my student to continue to work on the surface reaction. So that will be more realistic for the formation of this. Now I move to the nanotechnology. At the beginning, I said, okay, there's many ways to get a nanoparticle. How about for our civil engineering? Can we have some innovative method to get nanoparticle? The answer is yes. Very simple. You put cement particle into large amount of water, and then you control the environmental of this reaction. For example, temperature very close to zero. And then we found cement particle can release the calcium ion, okay, just like we discussed earlier. And finally, they can form very small calcium hydroxide. How big? 5 nanometers, and very uniformly distributed in the solution. Very good. And we tried this on the magnesium. And also we found we can get the similar phenomenon. We can get about 2 nanometer to 3 nanometers particle from this magnesium. So we said, okay, this is a reliable method. So we can use this method to produce nanoparticle, use our common utilize the cement particle. And this is a very cheap, okay, very simple operation, okay. So someone asked, okay, if you got this, do you have any, you see the big advantage? So we compare with the other nanoparticle here. So we found all the, you see the surface area is the smallest, and you see the particle volume is the smallest. So that means, and the same volume, we have more this cement produced nanoparticle. More particles, there's more effect in restrain or the reinforce the material. So we are utilize this nanoparticle generated. So first we did the research to produce one kind of material called, you see the hydrogel. The hydrogel basically is kind of polymer with water, about 80% water, okay, 15 to about 20 about this the polymer. So when they you see the before this polymerization, we utilize the monomer and initiate, okay, we let they combined with all, you see the nanoparticle generated. So and we produce this kind of hydrogel. And this is some photos. You can see it's very transparent. And the microstructure is great. And you can also find some in the string. Okay, you can find some small. You see the joint. This joint is made by this nanoparticle. It is amazing. Okay, after we utilize this nanoparticle to reinforce this hydrogel, the mechanical performance is exceptional good. Okay, so On the compressed side, we have three. The top one is hydrogel without any nanoparticle. The middle one is with the, you see we purchased this nanoparticle from the commercial side. So this is kind of organic. And the bottom one is the hydrogel reinforced with our, you see the cement generated nanoparticle. If you pay attention, you can see for the first one, top one, when you compress, they become very thin. But when you remove, they cannot recover. That means it completely lost their elasticity. For the second, you see, after remove the force, all the hydrogel was broken. It's very, very, you see the brittle, okay? Only for the bottom one, after you remove the force, they will be recovered to the original side. So that means they have very good elasticity. And for this tension side, okay, so we found the maxima tension can be 100 times over the original side. Okay, so you can see it's without broken. Okay, so this is a very good elasticity. So we have one, you see the article published in the Nature Communications. Okay, so we compared with the hydrogel reinforced with other nanoparticles. You can see with our cement produced nanoparticles, the amount we utilize is small. And the strength improvement almost the highest, and elongation is the highest. So that means we do have the good results, utilize cement produced nanoparticle to reinforce the hydrogel. So currently, okay, we are utilize this kind of hydrogel for the application. So one of the application we can utilize for this medical and also for some adult, you see that. So in Dongguan and somewhere, there's some factory, they produce this. Currently, they use, you see the, some is the other material, okay, and what they found, our material is much cheap and is have better elasticity. And another, okay, we use this hydrogel to produce this kind of super absorption, you see the material. So the highest, you see the absorption for the, you see the hydrogel we produce with this nanoparticle is 13,000. So that is the highest we found in the literature. That's about 2 or 3 times than what reported. Okay. So why it can have, because this the microstructure you can see they have this very special this kind of you see the valley and something like a hair growing on. So that's help the absorption. So one full application is that we can use that for this the soil you see the improvement. So we put some our you see the generated hydrogel and the commercial available gel and some you see the without handling. So you can see, okay, so for our hydrogel can you see the keep about 40% of is water in 6 months, but the other. And also for the plant, okay, without the hydrogel, okay, so basically the very difficult for the you see the for the seed to you see the green, and commercial available is only about 40%, but for this our you see the hydrogel modified about 100%. So this is that. And also we utilize this in our the concrete. We use that you see the internal Q material. Okay. So because this material not only for this the fresh water and also for this salt water, okay, we can use it about 300 times. So that's good. So we did the tests for the concrete blocks, okay, at this the 2% is the addition of there's you see the final strength loss only about that, but for the commercial products is about 20, okay, and also we can reduce the shrinkage by 20%. The commercial products only 5.5%. So this is so we currently also push the application of this in the home. And also we utilize this kind of you see the gel and to produce other products for the application. For example, we have this heavy you see the metal adsorption, and use this the non-contact you see the transducers, and we have this kind of you see the high elasticity, but with kind of you see the oil replace the water for the application, something like the base isolation, and we also use that for the growing of the cells. So the result is also good. So because it can be a soft, you see the organ for this the human being. Okay, so this is now on the other sorts, we use our to you see the nanoparticle to reinforce the hydrogel. Now we can we use that to you see the reinforce our cement-based material. So we did the same thing. We put the monomer, initiate, accelerator, and we mix with the cement slurry and the cut samples. And during the hydration, we are expected is an in situ polymerization happened, and then it can form second network in the cement-based material. So this is one of my students' PhD thesis. What he did, use you see the 0.3%, 0.6%, and until 5% of this the monomer. To investigate, is there any chemical bond formed between these the hydrogel and cement hydration? We use a TOF okay, to check, and the result looks very good. Okay, so the hydrogel have you see the N, and you have the side. You see the for the both the N and the side group. You can see the yellow one, the red one. Okay, the red one is without this the addition of this the hydrogel. The black is, so you can that have very high peak on both the side group and N group. So that means we do found the chemical bond between hydration products and hydrogel. And then we did the fractional test. Okay, you can see the best results we obtained. That's about you see the 27 megapascal at 28 days, and for this reference is only 6, so it's very high. And meantime, there's no much reduction in the compressive. And then in the University of Macao, I attended this work into the concrete, and one of my students right now in the Singapore, okay, he did for concrete, also used the same technique, use this monomer, and what I found very interesting is by adding this monomer, so that the hydration heat history also different. It's the peak is you see the before the reference specimen and also low. And then you can see after you see the good, you see the reaction water is very clean. And then we check the fractional strength. The best one can increase about 60% for the concrete, and then the toughness can increase about 2.7%. In the meantime, okay, they have this the good you see the result in this the so-called you see the durability parameter. Here we use the core rate diffusion. Okay, you can see the better one is only about half of that without this addition of the monomer. Okay. So next I'll talk about for the high modulus concrete. This is one I done at HKUST. So what we did, we add this the nano silica into this the concrete. We try to produce the concrete with the high modulus. So we started from this commercial mixing design. This is from you see the government. Okay, so at that time we are the partner. And then we are modify that formula into this high modulus concrete formula. And then what we found, okay, by adding this nano particles, you can use the enrich the use the transition room, and you can increase the modulus into about 53.5 gigapascal. And if you do the structural test, the beam midpoint deformation for the high modulus is about 1/3 of this the normal concrete. So here is a video.
Construction of tall buildings is an unstoppable trend all over the world in recent several decades, especially in Hong Kong. In 2017, Hong Kong is ranked #1 city by number of 150-meter or higher completed buildings, 25% more than the second, New York City. One major driving is the limit of available land. Therefore, the city expanded vertically, which requires a rigid structural frame to sustain lateral loadings like wind loads. If we look at the materials used for construction of tall buildings, 85% are using concrete. When designing tall buildings, structural engineers have to use large cross-section area of beams and columns to control the structural deformation. The Construction Industry Council noticed the problem and spotted the significance of concrete technology. They sponsored a research project on the development and application of high modulus concrete by Gammon Construction Limited and the Hong Kong University of Science and Technology in 2013.
Concrete have two important properties. One is the strength, especially the compressive strength. Another is the stiffness. Relatively, it's easier to develop high-strength concrete, but not for the high modulus concrete.
However, concrete modulus increases to a much less extent than compressive strength according to the Code of Practice for Structural Use of Concrete 2013. This study is quite challenging. The first stage of this innovation is to optimize mix proportions for high modulus concrete. A new type of crushed rock aggregate was identified, and the ratios among each constituent material were optimized. To improve concrete properties and enhance mixing efficiency, ultrasonic mixing technique was firstly applied in producing concrete. It is clear that the interfacial transition zone between aggregate and cement paste becomes much better after ultrasonication during mixing. High modulus concrete, developed by Gammon and HKUST, has 20% higher stiffness than normal concrete in the Code of Practice. Therefore, up to 20% materials can be saved to maintain the original structural stiffness. It also shows excellent dimensional stability properties in both early age and long term. Shrinkage, creep, and weight loss all decrease compared with normal concrete. Besides, selected rock type does not have alkali aggregate reaction risks at all, which affects the durability of concrete structure. Large-scale beam test results indicate that high modulus concrete leads to near 55% reduction of mid-span deflection. It verifies the advantages of deformation control. High modulus concrete has proved workability, mechanical, chemical, and durability properties, and is ready for structural engineers' design and industry scale. CIC is also ready to lead us for carry-out pioneering construction projects to harvest the benefits in the sense of sustainability and for sustainable built environment.
In building design, we had to control diffraction of the buildings. If we would like to use such kind of concrete, eventually the cross sections, such as columns, walls, the cross section will be greatly reduced, thus saving a lot.
Overall, 15 to 20% materials can be saved if this high modulus concrete is utilized for tall buildings. It is bringing tremendous benefits to construction sustainability and will lead to an unprecedented revolution in construction industry.
So we're going to, yeah. So next we talk about how to use this physics law to develop some, you see, the innovative material. So this is the so-called external wall system produced. Okay, so basically compose two parts. One is inorganic reflective heat insulation coating. Another is a structural heat insulated wall panel with the addition of the PCM. So by utilizing, for example, we produce a roof. So the first we have the coating when the sunlight come, okay, most of the heat reflected. And second, we have the panel with the PCM inside, so they can storage some latent heat, reduce the heat, go to the room, so we can keep the cool temperature inside. So this reflecting material we develop according to this refract, you see the equations. So we have the N1 T1 plus N2 T2 equal to lambda over 2. The N is the refractive index of material, T is the thickness. So when we design the material, if we get many layers, can reach this, you see the formula, the V with is wavelength lambda cannot penetrate. So we developed this, we did this reflection test, and you can see the red one, this material we developed. So basically it reach about 90% reflection for the range from visible to this you see the you see the infrared here. So this is the the first thing we did, it's a very simple test. Okay, we have a 150 diameter cylinder of concrete inside, make it hollow with 100 centimeters concrete mold. And then we are on the you see the surface, we use a different coating material, and we use the infrared to shoot and measure the temperature inside. So the results showed very good. The highest can you see the get is 41%. You see the improvement. And then we are utilize you see the testing method by utilize also use the infrared shoot, and on the you see on the box top we have the hole. We with the plate with and without the coating, we measure the temperature at the bottom side, and here is the black is without coating, and the red one is the commercial coating, and the blue one is the coating we developed. It showed very good, and they showed the you see the bonding between this the coating material and the substrate, and we did this you see the UV test. Okay, for the material with the organic, and you can see they have a very heavy damage after 800 hours UV radiation. But for our material, almost there's no any change after. So we did some, you see the site test. So this on the, you know, in Hong Kong, mainly you see the construction site use the container as the office, okay? So this is on the construction side of the garment. So we did a measurement. You can see one with our coating, another without. So you can see for about like 3 months, you can read the coating, you can see about 552 you see the kilowatts hour. So that's quite good, you see the saving for that. And then we are develop this kind of extruded material, and with we add this PCM. You can see you can reduce the temperature difference between the internal and external. And also we can have the good strength for this bending strength more than 2 megapascal. We had some using the manufacturer trial and did some using the design for the real structure like currently for the MRC. Okay. Now we are talk about the sound. You see the insulation material. Okay. We know the sound is very difficult to block for the low frequency because there's a Mass law. If this low frequency, the thickness of the wall must be increased to block this kind of wave. However, at HKU, we develop according to this use physics law, and we use a composite material, okay, for the different composition of this material, and we can use the tune the density, effective density of the composite material. And this composite density is with the wave penetrated and there's the self, you see the frequency, okay. So by adjust this number, we can get almost zero or negative the effective, you see the density, and then the wave corresponding to that frequency cannot penetrate according to this physics. So we did the basic experiment. So you can see from here is a very good, you see the verification. So we did a many material, we did the concrete, gypsum board, and some composite, and also with this our material called ISM. Okay, you can see between the 140 to 240 hertz is very low frequency. We have the peak about 45 dB, but the normal using material is less than 25. So that means they have 100 times different in the block of this low frequency. And later we generated the second direct, you see the generation we use for this the 3x3 wall test, and the test results showed also very good. You can see at this low frequency, we have about 3 dB. Then we have the cement-based material. This is work we are also, you see, the developed at USG for many. So basically, we use the powder from piezoelectrical material mixed with the cement at you see some guidance for the fit. And then we produce this transducer. You can see it's very good to follow the force. On the top, the red one is the square, is for applied by this MTS, and the bottom for the you see the black. That's the signal output of the transducer. We also you see the put the transducer into the reinforced beam, and we are use the 4 different frequency, 4 different amplitude to generate this zigzag you see load pattern, and we found the transducer inside the beam can follow exactly the pattern of this loading. So that means it's very reliable. And we did that use for the high traffic monitoring. And so when the you see vehicle passing through can give the speed and the weight of the. And also we are utilize this for the high-speed rail detection for the crack, because high-speed rail they have very long, you see the time and turning out because 80 to 100 meters. So they are very afraid that any crack will create some safety problem. So this is the one project originally with Xinan Jiaoda and PolyU, and then they met a lot of difficulty. They called me, so I said, okay, we can use our the transducer to try. And then we put the transducer on the and then we found it's really very good. Okay, you see for this two you see a spectrum. The one is for without crack, another with crack. You can see there's quite different from this spectrum. And then we utilize this IO11, to you see indicate there's a crack. So finally, they passing the you see the examination from you see the real department, military of real at that time they not become the company yet, and now it's it produce you see the product for the application in the whole China. And this you see the measurement is called non-contact resistivity, or you see the measurement. Because sometimes we need to measure the resistivity of the concrete because it's a porous material and use the resistivity to interpret the concrete property. Before it's always used, you see it's anode, the cut uses is select electrode, and with this contact, there's a lot of problem. At least you cannot get accurate. So I developed this non-contact based on the electromagnetic, you see the mechanism. So in this, you see basically, we have you see the this something like the transformer. We have this iron core and the so they can generate you see the magnetic field in this the core, and this magnetic field can generate an electronic field in this circular ring. This circular ring is produced by the concrete or cement-based material, and then we use the non-contact you see the current meter to measure current, and then we can calculate get the so that the whole thing no contact. So my first PhD students use this get their PhD degree. So what he found, this method is very you see the reliable. So for the cement paste 3.4.5 watt cement ratio. So they have a similar of this the resistive time curve, and they all have this lowest point. And later on, we interpret the lowest point, in fact, is the starting point for the hydration. And then you see the second PhD student doing this. The main you see the contribution of her work is he utilized this the non-contact resistivity to indicate the you see the setting time for concrete, because for setting time for concrete is very difficult. You need to see the coarse angle out only you see the model, and then you do penetration. So it's very time consuming and it's labor consumed. However, by utilizing this non-contact, if we use this the characteristic 2 point, we can predict very well for this the initial and final setting time for concrete. My third students use this technique to use them to measure the porosity inside the concrete, the total porosity. So that's the formula he developed, and the F is a factor we call you see the formation factor. That is the ratio of the resistivity in the solution to the resistivity of the concrete at that time. So you can prediction of this is very accurate. You can see the red curve is our prediction. All the dots is experimental results from many different research. My fourth student use this technique. He attended is the measurement for the resistivity to it's the more frequency. Is called impact impedance. The impedance need more frequency and need you see you measure both the real and the imaginary part. So what you can measure by the different frequency, they have the same point at this lowest. You see that. That is very good indication. And later on, he developed use this to distinguish the pore size inside concrete by utilizing this. And when large students use this technique to utilize to measure, you see the Nyquist plot for this cement-based material. A very good thing you can see for all the plot is goes to the 0 because there's no contact, so there's no any use the capacity you see the effect, so it can go to the 0. Okay. Okay, so finally, I talk about this the wind power generation. Okay, so this diagram tells in fact for all of the Earth, which are not you see like you can see the energy from you see the solar and the energy from the wind is much larger than the global consumption currently about 15 tera. So for wind only, recently, we have a quite, you see the increase in this development for, So even now, we can see the globally, we have this 117 gigawatts of new, and then by the year of 2023, it's an increase about 23 gigawatts. If we divided this by this 870 tera, so it's only about 0.1%. So it's still very small. Okay. So to increase the wind electricity, we need to increase the wind turbine size. Okay. So here we show them two different. One is the horizontal axis, another is vertical axis. So this is a trend for the you see the size increase. You can see currently the diameter for the you see the blade sweep you can reach about 250 meters. So by increase the size, the problem is that the vertical weight is also increased, but also with a cubic, for this large, you see the so when you increase the 1 meter from 80 to 81, and then the weight will be the cubic of the 81. So that is a very big burden for the material, especially for the you see the bearing. So the vertical axis wind turbine currently is a very small commercial application. What is the reason? Because you see the this vertical when in turn it can generate a very heavy vibration, and this vibration can cause fatigue many problem. So if we can resolve this problem, we can develop this vertical wind turbine because they have a lot of advantage. So how to resolve this? So we develop is a new kind of you see the structure for the vertical wind turbine. This new structure is utilize the liquid as a supporting force, and the foundation something like the ball shape. So this is advantage for this you see the new you see wind turbine. I do not. So this is the very beginning of development. So you can see it just like this is the ball, and then you put this blade, and that's connected with that, and use the water to. So you can for the simple you see the test. Even you use about you can use the say rotate. And with this, okay, you can see the electricity generated. And when I used to give a talk on this, always people ask me, I say, so Professor Lee, you are the concrete guy. Why are you doing this? I said, okay, we have to come back to the concrete. So how to come back? We use the concrete to produce the blade and the structural form. This is the structural form for this kind of, because this kind of is the new wind turbine give us the possibility to utilize the concrete. So this is the wind turbine test we did at HKUST before I moved to UM. So you can see very far. Oh, here comes the concrete, concrete blade. It works also very well. It works very powerful. And then when I moved to the UM, okay, well, I have the you see the financial support to build up this you see the wind turbine put into the campus. So after it's 5 years operation, the one of the good thing I found is that this kind of wind turbine is very good for the resistance of the typhoon. Okay. So why? Because when you see the typhoon come, okay, this just change is rotate energy, okay? So they do not against the typhoon, but the horizontal, okay, they move like this way. So when the typhoon comes, it's just against. It's very easy to be damaged. But in our country, so every year we have so many typhoons, okay? So if we utilize this for the ocean wind, you see the electricity generation, then have very good So currently I still work with University of Guangzhou, okay, to continue this project. I hope in the future we can move this from the lab into the ocean for the real you see the electricity generation. So here I just want to do a small ad. Okay, so you see the root the advanced concrete technology for the first in the year of 2011. Okay, and then in the year of 2022. Okay, you see the publisher you send me the email. You said okay, send your book is have a good response. Do you have any interest for a second edition? I thought it's too much work. Okay, I talked with my students. I said, if you want, we go ahead for the second edition. So I got help from Xiangming Zhou in the British now UK, and Hong Yan Ma now in the US, also in the Missouri University. Hodong Shuai, okay, in Qingdao University of Science. So we are in the year of 23, we are published second edition. We add a lot of things like it's carbon neutral and is also the quantum mechanics for the concrete. So the page is 110 more than the first edition. So I think, okay, if you have an interest, please take a look at on the new edition. Okay. And also I would thank my students, and without their effort, I cannot have so many the material to produce to present here. So and also my students also like hiking with me. So every year we have at least twice. So we right now we go all the small hills in Macao, so we move all the hiking into the Zhuhai. Okay, so just a week ago we completed another the hiking. Oh, okay, with this, I complete my presentation. Thank you for your attention.